yet, you know. After thinking about it for a while, I decided that we just do some problems. Right? And anyone who has a question on some problem that he's having problems with, this is the time to bring it up with the board and get it. At the end of the session, we have a lab that we're going to do, lab number 5. And yesterday, I set it up already. I tested it, so it's not something that's going to take us very long, you know, because it's all connected, it's all done. I did that to maximize the time that we need to do the review on, okay? So, I don't have something specifically.
Can you just do a highlight of chapter 3?
Highlight of chapter 3, let's start with the highlight of chapter 3 then, okay? Good question, good suggestion, I should say.
The first homework problem was straightforward, but it took a long time.
The first problem of chapter 3?
326 that you gave us.
Okay, maybe that's another problem maybe that we can look at, you know?
Yeah.
You know, that'd be a good idea to at least explore that, because you're gonna have something probably that's along those lines.
Something similar, I'm sure, if you gave it to us.
So what was chapter 3 about? Chapter 3 was about damped vibration, which is typically defined with mx dot plus cx dot plus kx equals function of time, but not just any function of time. A very specific function of time, which is a harmonic function of the form f naught cosine omega t. That's really what chapter 3 is all about, right? And the big question is, if you have a mass attached to a string like this, this is C, this is K, this is M, and you're applying this force, let's say this is the equilibrium position, and you're applying this F naught cosine omega t to this mass, pushing it back and forth. The big question is, what is x of t? In other words, how is this mass going to respond? That's the basic premise of the problem. Okay? We have this situation, we apply this force, and our big question is that the big question is, what is this? What is x? So, looking at the equation back then, we recognize that it is a non-homogeneous second order differential equation. From our knowledge of differential equations, we know that the solution is going to be a combination of two solutions, namely the homogeneous solution plus a
Particular
solution.
Sorry.
I keep counting to 10 and I forget that.
Oh, yes.
How are you feeling?
I kept,
Should you be wearing a mask?
No, she told us earlier that she was coming. It was like, fight for the chairs.
Yeah.
Let me
I'm back.
unload this stuff. Here. Okay. So the big question then is what this is. And X homogeneous is the solution to, so XH is solution to what? Mx dot plus Cx dot plus Kx equal to 0, because that's the homogeneous one. And we have learned from chapter 2 that one form of this solution, one form that this solution can take is that xht is equal to maybe C1 cosine omega nt plus C2 sine omega nt. Where, by the way, omega n is simply the square root of k over n. Now, this solution typically is a homogeneous solution, and then we have a particular solution. Particular solution in general will take up a form that depends on how the equation actually looks like. Okay? So, but the homogeneous solution is like this. Then we went on and said, okay, let's look at one simpler case, in which case the problem is undamped, right? Undamped means that C is equal to 0. So, in this particular case, then my equation becomes mx dot dot plus kx is equal to f0 cosine omega t. Now notice that this omega has nothing to do with this omega. There are two, many times you have forced vibration, always keep in mind that you have two omegas that are not necessarily the same.
So
In fact, you don't want them to be the same.
undamped, is there always a force vibration?
Because omega
Pardon?
n is the natural frequency, right?
Yeah, so omega n is the natural frequency, meaning it's the free vibration. That's the type of vibration that, even if you have damping or you don't have damping, it's a type of vibration that's, what is it? It's a characteristic of the system, right? So if you let it go, that's how it's going to vibrate. You have a question?
So, I forgot my question already. No, it's okay. It'll come back.
Isn't there like omega damped, and then omega natural? Or
Yeah.
is it?
Yeah, that's,
So it's free.
when you go back to the free damped vibration, free damped vibration. Okay? Free damped vibration is actually given by this equation, right? Is equal to 0, and then what we determine, the critical part of the free vibration, free damped vibration, is we have how many outcomes? If I have a damped system just
Oh, you
like
have
this
three.
one and I
It can
pull
be
it
over,
and I let it
vertically,
go.
or under, right?
That's right, the three
Okay.
possibilities, right? So the first one is under damped, critically damped, and over damped. Okay? How do I determine if something is under damped, critically damped, or over damped?
The ratio
It's one.
of C to CC.
It's a ratio of C over CC, right? So I gave you an example last week. So if you are given a problem like this, the first thing you can figure out is you know what C is, because it's, you just read it directly off the equation, and then CC is equal to what?
2 root km.
2 root km, exactly. So you know the spring stiffness, you know this, you can find CC, right? Now if C is less than CC, that's the under damped, C less than CC, C equal to CC, and C is greater than CC, right? Now, among these three, there is, how many of responses have some oscillations? How many have? Just the end of it, just one out of the three. Okay, not two. So just one out of the three has a damped vibration, and that one, as it vibrates, it will vibrate with what frequency?
The omega D.
Omega D, exactly. That's the damped frequency, and the damped frequency omega D is equal to
1 minus zeta squared times omega n.
omega squared, isn't it squared?
1 minus, yeah, square root of 1 minus.
Yeah.
Where zeta is what? C over CC. There you go. You know, that's kind of in a nutshell, just to talk. I'm glad you brought that up, because there are
Review of
essentially
class.
3 frequencies that you have to think about. There is omega n, which is a characteristic of the system. There is omega d, that's for free vibration, right? As it vibrates and comes to a stop, for only for under damped, obviously. That's omega d. And when you talk about forced vibration, then it's just omega, right? So we took this little,
Segue.
yeah.
Okay.
So under damped, C is equal to 0, we come in like this, right? So the homogeneous solution is still kind of in this form, right? But what is the particular solution? What form could it take if you are forcing it? Remember, the forcing solution, the steady state solution, the particular solution is always the steady state solution, right? It always has the same frequency as the forcing function, right? Now, if the forcing function looks like this, then this one will be just simply some x, which is some, what does x represent that way? Amplitude, you know? So I don't know how much this mass is going to be jumping up and down, right? So we'll just call it x, right? Times, if this one is cosine omega t, this better be also cosine omega t. Why is that? Because there is no damping, and if I have a cosine, when you take a second derivative of a cosine, what do you end up with? It's a cosine also. See? Cosine omega t. This one will also have a cosine omega t. This one has a cosine omega t, so it can cancel out. That's pretty much the reason why. Now, when we do this, obviously xp will be what? Minus omega x sine omega t. And then x dot dot p is equal to minus omega squared x cosine omega t. Remember, one of the big questions in this type of problem is how do we determine x? What is the amplitude? Because we know what the frequency is, right? The frequency will be the frequency of this force, right? So I just need to find what is the amplitude, okay? When you replace this, what did I write here? xd equals. So if I substitute the value of xp into this equation right here, the undamped equation, I will end up with minus, so m times x dot dot, which is minus m omega squared capital X cosine omega t, and then plus kx, x is this, so plus k capital X again, cosine omega t is equal to f0 cosine omega t.
Wait, is it not negative? Wait. Oh, nope, never mind.
Are we good?
I think so.
Okay. Now, because this equation has to apply for all times, right? I can simplify by cosine omega t, right? And then end up with what? Capital X times k minus m omega squared is equal to f naught, which means that capital X, which is equal to f naught divided by k minus omega squared, okay? That's one form of the amplitude. Sometimes we also divide it by what? We divide by k on both sides, okay? And this is nothing more than delta static, right? 1 minus omega squared over omega n squared. So isn't this cool, you know? You can find the amplitude immediately, you know, if you are given a problem like this and try to figure out the situation. Now, you can find it if obviously omega is not equal to omega naught, because if that's equal to omega naught, you're in trouble,
Okay, let's do that.
right? So first of all, looking at this again as a solution,
When you say omega naught, you mean omega n?
omega n, yes.
Yeah, because otherwise it'd be 0 and you can't divide by 0.
Exactly, yeah. Now, if omega is less than omega n, look at this equation. If omega is less than omega n, is the denominator here positive or negative?
It's positive.
Denominator is positive, right? That means that, excuse me, that x and delta st will have the same sign, right? Both of them are positive, right? That means that the response is in phase with f. In phase. See, f is increasing, the response is increasing. F is decreasing, the force is decreasing, right? In phase, right? And we had a plot like that, I think, in which we were showing f as a function of t and x as a function of t. But if the frequency here is greater than omega n, then the denominator is negative. That means that the response is
Out of phase.
out of phase. By how much? 180 degrees with f. In other words, when one goes up, the other one goes down. Okay. And then looking at this, when the frequency of the applied force, if I have a mass and I vibrate it with as high frequency as I could, what happens to the response?
It gets crazy, right?
Now look at this. When omega goes big, what happens to the denominator? If omega approaches infinity, let's say it goes big, right? Denominator goes to infinity, right? That means that x will approach what? Something divided by infinity is zero. Okay? That means that the response of something, when the frequency is really high, you're not going to get the darn mass to move at all, or very little. Okay? That's how you read these type of results. That's why we had that little plot, if you guys remember, when, if this is omega n, right? Usually you have something that kind of increases like this, right? And then here it comes in and goes like that, right? So this is omega, I guess omega, or omega over omega n, where the value here is 1, right? And this is x. See how the amplitude, and this is 1, obviously, because when omega is equal to 0, the denominator is equal to 1. That means that the amplitude will equal to the static deflection. Okay, so that's kind of the big idea behind this chapter. Now, there is one additional step we have to talk about. Here we talked about the homogeneous solution. Here we talked about the particular solution, right? So the total solution will be what?
Both of them together.
Both of them together, meaning that C1 cosine omega n t, okay, plus C2 sine omega n t plus xp. Now what is xp? xp is x, which is, I guess, f0 over k minus m omega squared times cosine omega t. So this is how my mass is going to respond. It's the sum of three sum of three harmonics. How many unknowns do we have here? Two unknowns, which are C1 and C2, and how do we define those? How do we determine those? Is by applying
Initial conditions.
initial conditions. Now,
Correct.
the initial condition will be with x naught and x dot naught. So let's do this. Before I go, I have to find what is x dot t, which happens to be here minus C1 omega n sine, right? Sine omega n t and then here plus C2 omega n cosine omega n t, and then here minus, right? F0 omega, right? Divided by k minus m omega squared sine omega t. That's why it's, you know, it's easier to rederive this rather than to look for it, right? It's just a derivation of a cosine and sine. Now, the last step is to apply the boundary conditions, right? At t equal to 0, x is equal to x naught, okay? Which is equal to, so this is the critical part here. Critical part. When I apply t equal to 0 here, what do I get?
C1.
Just C1, there is no cos, because cosine 0 is 1. So it's gonna be just C1. How about this? 0. How about this? Just F naught
Just
over
omega x.
K minus M omega squared. Okay. How about the second one? At t equal to 0, x dot is equal to x dot 0. Okay? Which is, come back now to this equation. The first term,
0.
no contribution. Second term would be C2 omega n, cosine 0, which is 1, and this one, no contribution. So from this equation here, I can figure out what my C1 is, right? Which is x naught minus F0 over K minus M omega squared. And then C2 is simply equal to x dot 0 divided by omega n. Now you have the general solution.
So like we could use that for any for any of our problems. Because I think on that last test you said, remember you made those general solutions, don't use those.
Yeah, because if somebody comes in, they're just for the heck of it, okay? There are different forms of this harmonic equation. If this equation was a sine, let's just say it's a sine.
Everything would be turned around.
So, would this change? Would the homogeneous change?
Homogeneous would not.
Would not. You still get C1 cosine omega nt plus C2 sine omega nt.
Right.
The only part that's going to change is the particular solution. If this force was F naught sine omega t, let's pretend, I'm not gonna go there, but let's just pretend that. How is your particular solution gonna look like?
Sine and
It's gonna be just capital X sine omega t. It has to follow whatever you have on the right-hand side.
Okay.
Now, because it's going to be the sine, right? Now you have to apply it. Obviously, when you apply the equation, everything is probably going to drop off, you know, with a sine, most likely, right? The only part that may come into the game is really here. Because now you're gonna come in with sine omega t, right? So when you apply when you take the derivative, this becomes cosine omega t. So you may have just a little variation in the values of C1 and C2.
You have to be careful when you're starting.
Okay? So if your driving equation, if your forcing function is in this form, I have no problem you using those equations because they've been developed already.
Okay.
But
if
it-
it's in sine.
If
then
it's
you
in
might
sine,
want
but
to
we
If
could
it's a
do, we
sine-
could do the whole thing in sine and have either
Yeah.
way.
Because the book actually goes back and does something with cosine omega t plus phi. Even for this, it changes this into some C1 cosine omega t plus phi, and therefore, you know, finding the phase. Different solutions, different ways.
The negative m omega squared x, that equation comes from applying the two derivations of the particular solution, right? To back to the.
Are you talking about this one here?
No, the one up from it. This,
Sorry.
this equation comes from applying these two back
Yes,
to this. Okay.
yes, yes,
Okay.
yes. This equation, yes, very good. Here we have our differential equation. This is what we have assumed the solution to look like. Before I plug it into this equation, I have to figure out what x dot dot is going to be. That's what I did here. I went from the function to its first derivative to its second derivative. Then I said, okay, let me go back to here and replace x dot dot by this big guy.
Gotcha, okay.
That means you're gonna have, that's where the m minus m omega 2 is gonna come. And then I simplified, then I came up with this.
So this is, all these only apply when you,
This only applies when the forcing function is in this form.
yeah, I saw the undamped, but then I realized it's only when you're solving to the homogeneous. And then when you're doing the particular, so.
Yeah,
Okay.
so this is for undamped, okay? Now when you go damped,
Even more fun,
it's more, yeah, when you go damped,
when you got an e to negative 2
so-
or something.
Before you erase that.
I don't have a lot of room. So if you wanna take a picture of this.
Someone else's.
For a cost.
The only thing that's gonna come into play when you have damped vibration is and again, just before I go any further, remember as omega approaches omega n, you know, you see that the amplitude just goes crazy. That's what resonance is all about, okay? That's why we try to avoid this frequency here as the forcing function. As far as possible from it would be great. Now, if my problem is now damped, if my problem is damped, then obviously I'm going to have a different solution because I'm going to have C is different than 0. That means mx dot dot plus cx dot plus kx equals to this, right? Now here, I cannot do this. Why?
Another factor in there.
Because you don't, yeah, you need.
Because if I take the first derivative of this guy, I'm gonna get a sine.
Yeah.
Then when I take the second derivative, I still get a cosine. So at the end of the day, I'm gonna have a cosine here, cosine here, cosine here. But this is a party pooper, you know, it's a sine, you know, it's not gonna do anything, right?
Yeah.
So the only way to get around that is to just be more general and saying it's omega t. I don't know what we did last time, is it plus phi or minus phi? You guys remember? I don't wanna do something different.
I think in the book it's both ways.
Book sucks.
I
Uh,
hate it.
We've learned that.
He's got a plus and a minus, the total response.
No, you cannot have plus or minus, it's probably
Under
uh,
3.1,
on page, it should be on page 271. It's x minus, it's cosine omega t minus phi.
yep, plus,
X cosine omega t minus. Now, the problem with this now is we don't only have to find the amplitude, but we have to also find the darn phase, okay? So I need to have damping, because when you have undamped, you're either in phase or 180 degrees, that's it, right? But when you have damping, that darn phase angle will change based upon how much damping you have. So how are you gonna figure this out? Well, again, the same problem is you have to figure out what is x dot p, which will be what? Minus omega x
Sorry.
sine omega t minus phi. And then what is x dot dot p? which is minus omega squared x cosine omega t minus phi. So what I need to do now is, remember, this particular solution has to satisfy this equation. That means I have to plug it into the equation, right? And if I plug it into the equation, what do I get? Same thing as we did before, m times this, which is minus m omega squared x cosine omega t minus phi. And then plus cx dot, x dot is this, that means minus c omega x sine omega t minus phi. And then plus kx plus k times x cosine omega t minus phi. The whole thing should equal to what? F naught cosine omega t, just cosine omega t, because that's still the forcing function. Yeah, that's a nightmare equation right there.
So it's not gonna be.
So
on the
how are
test.
we gonna figure out what the heck x is?
He
See,
said
for
last
n
week,
damped,
so very gonna be in.
for n damped, we were able to just cancel the whole thing, right? But now we can't. So what route should we take?
Google it.
Google? Now, it's gonna be a fairly long derivation, but
You gotta do the tangent bit, right?
no,
But you still have.
no, this is the way you're gonna do it. It's you take here, I'm gonna start it from there, minus m omega squared x. You need to use the trig identities.
No.
What's cos A minus B? Anyone remembers? Cos A minus B is cos A cos B plus sine A sine B. Right, so cos A minus B is, if I remember it correctly, cos A cos B plus sine A sine B. And then there is another trig identity that is important, is when you have sine A minus B. What would that be?
Sine A.
That would be sine A cos B minus cos A sine B.
Oh, are you gonna divide them and get tangent?
No, there's no, well, not yet. Now we had to do, but not yet. Yeah, that's for the easy part. So here you have minus this, so tell me what this cosine omega t minus phi is going to be. So it's going to be
So it's-
cos A minus B, that means cos A, cos omega t, cos phi, plus sine omega t sine phi. Okay, now we need to do this other one. Minus c omega capital X times, what's sine A minus B? We said it's sine
omega t,
cos phi,
cosine
right?
phi,
Minus cos
cosine
omega t sine phi.
Can you move out of the way for a minute?
Yeah, this is not a good room for having these long derivations, right? In fact, I think I need to clear up that right-hand side,
Yeah.
just to get myself a little bit of room
It
here.
just means no long derivations.
This just means no longer derivations on the test, right?
Yeah.
No, nobody's gonna ask you to derive things on the test, no.
Just use
No,
them.
This
one
is-
of these not be
Are
on the
you
test?
anybody? Are you gonna put one of these on the test then?
Hmm?
Are one of these gonna be on the test?
Like a damped.
A damped is going to, yeah, he
of
said
course,
last
that's-
week a damped was
But
going
not
to.
not deriving stuff.
Yeah,
So we'll have, there's a equation we could use.
That's why we need to look at some examples very
Right.
shortly,
Yeah.
just to see how that's being used.
Yeah, I'll get
This is
the
just in
equation here
response
just a minute.
to how it's done, you know. I was hoping somebody would say, yeah, don't do it, that's it, we know how.
Oh.
Nobody's saying that, so
Oh,
I
man.
cannot take that easy way out, okay? Cosine omega t cos phi time plus sine omega t sine phi is equal to f naught times cosine omega t.
Are you sure?
I think I'm sure on this one.
I'm not double.
Now what's my next step, you think?
You gotta combine like terms, you got cosine.
Combine like
cosine,
terms,
sine.
exactly. In other words, take everything that's got a cosine omega t and factor it there, out, right? So, okay, so let's start. So anything that's got cosine omega t, so what would it be? Minus m omega squared x cos phi, right?
Yeah.
This guy no. This guy no. How about this guy? Minus and minus becomes a plus. So it's gonna be plus c omega x sine phi, right? Anything else? Oh, there's another one here.
It's kx.
Plus k capital X cosine phi, right?
Yeah.
And that's it. And this whole thing is multiplying what? Cosine omega t. Now I need to group what? The sine terms. Plus, let's figure out what the sine are. First one is this guy, minus m omega squared x sine phi, right? And then this guy should be there also. So minus c omega x cosine phi. And then there is a term in here, right? Which is plus k capital X times what? Times sine phi. So this big term here times sine omega t is equal to f0 cosine omega t. Okay, so I've done all this. How is this gonna help me? Under what conditions is this equation satisfied for all t? Let me simplify something for you. If you have a cosine omega t, right? Do you agree this would be a, just something, right? And then plus b sine omega t is equal to c times cosine omega t. Under what conditions is this equation always true?
If the b sine omega equal 1, oh no, it's 0.
That's very good. Okay. Here, do I have any signs on the right, sine omega t on the right hand side? I don't. So this b better be equal to 0. I cannot say sine omega t is equal to 0 because omega is non-zero, t changes. So it's the factor that multiplies b, like this guy. This guy better be equal to 0. And how about this guy? What should it equal to, you think?
F cosine omega t.
Well,
Or
just
It's the same as both.
same as just f naught.
F naught.
You see, it's a one-to-one correspondence. It's like when you have two vectors that are equal, right? Vector AI plus BJ is equal to CI plus DJ, right? The only way those two vectors are equal is if what multiplies the I for this is the same as that, and the B and the J is the same. So that means that this group here is simply equal to
If not.
F naught. How many equations? 2 equations. How many unknowns am I trying to solve for? 2 unknowns, right? My unknowns are what? The x and phi, right? So if you look at the first one, for example, here, you're gonna end up with this equation that's equal to F0. So I could say that if I factor out, in fact, the let's see here. K minus K, yeah. So F0 here, I just want to write it in a form that is K minus M omega squared times cosine phi, right? Plus C omega sine phi, and this whole thing times x. That's exactly what's in the book, I think, on the equation. Of course, the book did not derive this, by the way, just so you know. Just gives you the answer here on page, on 327. It says x times k minus omega squared, x times k minus m omega squared times cosine phi plus c omega sine phi is equal to f naught. Look at equation 327. You will see where it's coming from. Of course, all this derivation is missing in the book, right?
Yeah.
Just for your.
It's not cool like you do.
And then, if you go to the next one.
What was the equation, 3.27?
3.27.
But it,
271.
Is it 271 or?
It's,
Page 271.
Oh, page 271, yes. And then, let me just write the last one. The last one is going to be, again, K minus M omega squared, K minus M omega squared sine phi. Oops. And then minus C omega cosine phi times x. That's equal to 0. Which is exactly what's in the book on 327.
So those are the two equations that we use to apply the initial conditions?
So those two equations, in fact, not those two equations. Now, you take it one step, because remember, our goal is to find what is x, what is phi, so you don't even need those two equations. You need the equation 328 and 329. Okay, those are the two key equations. Okay, solving for that. So remember, this is, I need to solve for x, right? So it tells me that x is equal to f naught. Well, in fact, you can look at it from here. What is x?
F naught divided by that big mass.
F naught divided by that big mass, right? Which is k minus m omega squared cosine phi plus c omega sine phi. You see that equation at the bottom of page 271?
Yeah.
So, but they just simplify it, 'cause they don't have cosine or sine in there. Equation 327 doesn't have.
Right. So we're gonna come to that in just a second, because you're right. You cannot have the cosine and a sine. So how are we gonna do this?
There's some other trick identity that we have to use.
Yeah, some
Tyler?
some tricky stuff. That's all right. So here you have your x, you have your, the sine is actually a function of the cosine in here, right? So, so how are we gonna solve this?
Gonna do something really sneaky and tricky.
Something really sneaky, that's what I'm thinking about. And I think I just thought of something. You know?
You're gonna have to think sneakily on the test.
Always.
I'm screwed.
So the so it's f0 k minus m omega squared cosine phi plus that sine phi, and what is that one? And then phi here, well, for this one it's still equal. If I said this is equal to 0, what does this mean? That means that k minus m omega squared, right? Sine phi is equal to c omega cosine phi, right? So we would divide both sides by cosine phi, and then by k minus m omega squared, k minus m omega squared. So this cancels, that cancels. The cosine and cosine cancel. That means that tangent of phi is equal to c omega over k minus m omega squared, right? That means that phi is equal to the arctangent of c omega over k minus m omega squared, which is, I think, equation 3.29.
So what does 3.28? Oh, that's for solving for x.
Yeah, for 3.28 is solving for s, which gonna take very long. What we need to do,
Don't do it.
Yeah.
you know, you need
Yeah,
to
I know.
isolate the sine and the cosine, and then what should we do?
We probably need to spend time practicing problems more than proving that it works, because we trust you.
Yeah, we just do that in 3D.
You know what? You know, that's a challenge, actually. How the heck do you get that? Can I erase this, or are we good?
Yeah. you can raise it.
Just a quick one, you know, I think I totally do it.
Right.
So if I take this equation and I square it, what do I get?
Which one?
F0 squared equals k minus m omega squared
Square.
cosine squared phi, right?
Uh-huh.
Of course, there is x, right? X squared, well, let's do the x at the end. Plus
C omega squared sine squared.
c squared omega squared sine squared of phi plus 2 times k minus m omega squared c omega, right? Sine phi cosine phi. And the whole thing is multiplying what?
X squared.
Okay.
You gotta co-square the sine square.
What's that? Yeah, you see, that's where we're getting at. And then if I square the second equation, what do I get? 0 equals
I'm getting nauseous.
K minus m omega
k minus
squared all
m
squared.
omega squared squared
Sine
sine
squared.
squared times phi plus c squared omega squared cosine squared of phi, right?
Y plus.
Now minus 2 times k minus m omega squared times c omega sine phi cosine phi, right? X squared equal to 0.
Were you getting
Where'd
that
you get
second
that
part
to?
of it?
Where do I get what?
The two. K
This
minus-
one here?
Yeah, all that part of it. Where was that coming from?
Oh, remember a plus b squared is
Oh,
equal to
okay.
a squared plus b squared plus 2ab. It's identity.
Identity.
Yeah. You guys have hopefully remember that, right?
don't have that.
A plus b times a minus, you guys remember that?
I'm gonna go cry now.
That a plus b squared, I'm assuming that this is,
A squared plus 2a believe plus b squared. Okay. 3b plus b squared.
and then a plus b times a minus b equals
A squared plus b squared.
minus b
Oh,
squared.
minus
These two are very, very common in engineering. So that's why I assumed.
Well, you know
All right.
what?
We're almost done.
Use it every.
What do you think I need to do now?
The one term.
Add them up. Exactly. If I add these, what do I get?
Oh.
This plus this.
Beautiful.
If I add this plus that, what do I get?
Sine squared is
2K
cosine squared is
So I just get the k minus m omega squared
squared.
squared.
Yeah.
Why? Because cosine squared plus sine squared is equal to 1. How about here?
Yeah.
So
Plus
2c squared.
c
omega
squared omega squared. That's it. Because sine squared plus cosine squared is equal to 1.
Wouldn't
But
it be two?
Wouldn't it be two,
C?
it's 2c squared omega squared, right?
Thank you. Plus 2
And then
c
2 in
squared.
the-
No, it's not plus 2.
Why?
No.
Right, that's one.
C squared plus this, and you factor out sine squared plus cosine squared. It should be just 1.
Well,
Why would it be 2?
I don't know, I guess. It's not.
Well, let me put it a long way. It's c squared omega squared sine squared phi plus, if I factor this, plus
Oh, yeah,
cosine
you factor,
squared.
okay.
Oh, I
So
see.
this is
Yeah.
1.
Yeah.
Yeah.
That's
Yeah,
one.
yeah.
Okay.
Got it.
Okay?
Your math is strong.
But this is the coup de grace though.
That's gonna
What
go to
happens to
0.
these two? They cancel out.
Yeah.
See? Yes. They cancel out. That means here I got here just x squared. Right? What does that mean for x? It's simply, now I take the square root, right? It's f naught divided by k minus m
There you go.
omega squared plus c2 omega squared.
That's why it's on
Oh,
C
yeah.
Cool, you just passed the
2.28.
exam.
Which is equation 3.28, right?
Yes.
All right. Never gonna do this again.
Now, here's the first thing.
Know how to do it.
Alright, well, that sounded good.
So,
No, we need to do some problems.
Oh,
Yeah, we need-
practice.
Yeah.
all right. so
Representative problems.
Yeah.
There you go.
Representative problem.
That might be on the test kind of problem.
Well, let's take a look at
Without extra long years.
chapter 3, right? Did you guys work the homework or not yet?
Yeah,
Some of it.
So, any questions about it?
pretty much what you're just doing here,
Well,
except
what
for
you did, yeah.
not derivations, but.
Yeah, I mean,
plugging
you're not
in.
gonna have derivations. You see, now you understand why the book does not go through all the derivations.
Yeah,
It just,
Be twice as thick.
yeah.
but this trick is not shown there, you know? It's, you gotta look at it and go like, that's probably what it is, and that's, I never done this before, by the way, rederive this.
I don't mind if they skip the derivations, it's when they skip steps in example problems.
You
Yeah,
know,
That's
oh,
what,
yeah.
that's what's tough. You're trying to follow along and learn, but they skip steps.
All right, so let's take a look at some random problems. Well, I think maybe chapter 3, there is one that. Two. Homework, chapter 2.
So the test is chapter 2 and 3 or just 3?
2 and 3, we haven't done 2.
We did.
Chapter 1, or
Portion of
the first
two we
test
did.
had chapter 2 on it.
What's that?
The
Yeah.
first test did have chapter 2 stuff on it.
Just a
Yeah.
bit lower.
Very little, almost nothing.
Last problem, the hardest problem was from chapter 2.
Yeah, but you know, there would, chapter 2 is free vibrations, I mean, what's it called? Yeah, free, and the other one is forced, so, but damped or undamped, so those are the, it's the same equation, you know? You're gonna have something about to figure out if it's, you know, under damped, over damped, critically damped type of situations. But just to reproduce the first problem here, which I thought was kind of interesting.
Which one are we doing?
It said that. Yes, it said that.
Because there is one thing that have you guys done problem 3, 4?
Not yet.
3, 4,
I
that's the
started
first
with
one?
3, 6.
Okay, did you encounter
Six is
any
not
problem
further
when you
than
did 3, 4?
Yeah, I had a question on it.
Okay, so let's, can I erase this thing now? This monstrosity here?
Yes, please.
All right.
3, 4, 3,
I got 3, 6, 3, 26, and 3,
what problem number 4 says, it says consider a mass spring system, spring mass, that means
I didn't do 4 now.
What number is this?
3, 6, 3, 4.
3, 4.
K and M, right? Where K is 4,000 newtons per meter, and M is 10 kilograms. Subject to the harmonic force, so F of T is equal to 400 cosine of 2T. It says find the total response. We're just gonna do one of them, right? Find total response if x naught equal to
Could you do B?
b,
Yeah, I had the problem.
x naught equal to 0, and x dot 0 equals 10. Okay? That's what b was.
Yeah.
All right, any volunteers?
Tyler?
I was the one who had the problem with it.
It's actually good when you're writing it on the
Actually-
board, working like that.
Is, in this case, is F of 0 the force 400 Newton meters?
Very good, good question. Good question. So when you have a function like this, what is F0 equal to?
400.
400.
Okay.
What is the omega equal to?
2.
In, not 20, it's
No,
2.
it's 4,
It's 2,
it's,
Square root of. No, it's
isn't it 2?
That's
Oh,
omega,
20,
not
sorry.
omega n.
No, it's 20T, thank you.
Oh.
Yeah, it's my fault, I didn't see that.
oh, it's 20 T, okay.
So
sorry.
it's 20, what unit?
Radians per second.
Radians per second. Radians per second, okay? So, let me throw in just a quick question here. If we want to write a differential equation that describes the motion of this mass, what would it be?
Would it be mx double dot plus kx equals 400 cos 20?
Exactly. So it would be 10 x dot dot plus
4,000.
4,000.
4,000 x equals 400 cosine 20.
Boom.
You see how you take something like that? Of course, it's not asked there, right? But the differential equation that describes this motion here is mx dot dot, which is 10 x dot dot plus kx, which is plus 4,000 x, is equal to f naught cosine 20t. Now, is this a damped or an undamped problem?
Undamped.
Undamped problem, right? So for an undamped problem, you really have to be very careful about what your forcing frequency is, which is 20, right? And how it compares to your natural frequency. So what is our natural frequency here equal to?
4,000 divided by
20,
20.
yeah.
Okay, so square root of k over m,
Which is 4,000.
4,000 divided by
10.
10, which is 20.
So
Problem.
Oh, it's critical.
So it's equal.
Rad per second.
So this one is equal to this one.
So, in that case,
So what happens to the response of a system like that when it's critically damped? Well, as a function of time, the amplitude just increases linearly until it goes to infinity. But you still have a response. So how are you going to find it? What equation are you going to be using? Because remember,
do you have to use 3.9?
because we talked before about, remember the response of this is still the response to, it's still the response to a what is it called?
It's equal to one, so we use different equations.
To the homogeneous, right? Plus the response to the, plus the response to the, so the response to the homogeneous is what? You know, C1 cosine omega nt, right? Which is cosine, cosine what? 20t plus C2 sine 20t, right? Plus the particular solution. But remember the particular solution, how it looked like before, right? I don't know if you guys remember, but when you had F0 cosine omega t, right? I think the response was in the form of what? X is equal to, sorry, xp is equal to capital X times
Cosine omega t.
cosine omega t, which is in this case 20t, right? Where x was equal to, was it f0 over k minus
Yeah, omega squared.
something like this, right?
Yeah.
Or in fact, we also wrote it as f0 divided by k, right? Divided by, what is it? 1
One
minus
omega
omega
squared.
squared over omega n squared. And
Would
this
that be
guy
r
would
squared?
typically call it delta statics, right? Divided by 1 minus omega squared over omega n squared.
Zero in this case.
Now, what is 0?
1 minus
Now,
1.
this is the problem.
That's the
For
problem, because
how am I gonna write my x?
Infinity.
I'm having something divided by infinity, something divided by 0. Something that, I don't know, maybe you know, something maybe you don't know from your integral calculus or differential calculus, I should say.
Don't know.
What do you do? That's where you do limits, right? The limits of functions.
Yeah.
When you take the limit and you have the top, the numerator and the denominator both go to 0. Or you have something divided by 0.
that's an
right?
indefinite interval.
Well, it's not definite integral, but it is, let's see. Let me just check something here quickly. The name of that. This is actually good because it's bringing back some memories.
I'm feeling really good about the test about that.
I'm not.
All right.
'Cause what do you do if you get, yeah.
That's why I felt.
So if we're faced with a problem like this, we need to write down all the stuff that we know that this the particular solution xh for the homogeneous is going to be xh, or it's going to be c1 cosine omega t, cosine omega nt plus t2 sine omega nt equals 0. I was a bit confused. You
Well, the
said
ratio
plus.
of omega to omega,
Omega over omega n is.
is 1, because
1.
it's 20 over 20, and
I don't know if
so-
you guys have your book or you don't have your book.
She does.
There is one part on page 265.
Will you sit next to me when we take the test?
I don't think
Okay.
they want me to.
There is one equation right
Super
there
fast.
where it says that
Oh my gosh. What do you think?
There it is.
you see at the bottom of that
3.9,
page,
Oh, wait, no.
2.65, I guess.
3.13.
3.13.
3.13, yeah. You see that equation when omega is equal to omega n is equal to 1, you know, from the previous equation of, the big equation, which is on that solution that we came up in general before, which we did earlier, which is x is equal to x naught, that's the initial condition, minus f naught over k minus m omega squared, right?
Yeah.
Times cosine omega nt, and then this is equation 3.9, by the way, plus x dot 0 over omega n, and we got these constants earlier when we applied the the initial conditions, sine omega nt, and then lastly, the particular solution will be looking like this because it has this f0 over k minus m omega squared times cosine omega t. That's the general solution, okay, which
That's
we
3.9.
developed earlier. That's equation 3.9. Okay, now, everything here is fine, right? But the problem is when omega, k, when omega is equal to omega n, this darn thing goes to 0. And we cannot have something divided by 0. And that's what brings up my thinking about the limits. When you take a limit and then it's something divided by 0, or if it's, you know, and then here you have obviously omega and equal to this, and
Well,
since it says since the last term of this equation takes an infinite form for omega equals omega n, that is the theorem. That's the one that I forgot the name of. It's called L'Hopital rule.
L'Hopital.
Does it ring a bell?
Yes.
L'Hopital?
Yes.
I'm sure you've heard of it.
Yes.
Yeah, now.
You know, so when you take the limit, when you have a problem like that, then you say, well, the limit, you know, the value of this will be also the limit when omega approaches omega n of the derivative of the top and the derivative of the bottom. Okay, always works. Okay, so on the next page, it is shown, you know, how to do this. You know, how to take the derivative of the top and the bottom and all that kind of stuff. And that's where you get the equation. I don't want to waste too much time on this.
3.15.
3.14, when you take the derivative of that using L'Hopital's rule, right?
Yep.
Omega t minus omega nt.
So when we get down
Well,
to-
the problem, you see, this is the situation. When omega n, this, just to kind of get you what the idea is, when omega is equal to omega n, it's almost like you have all that is grouped in one spot. Okay?
So, may I ask a question? When it's equal to 1, and they get down to that equation on page 266, 3.15, after they apply L'Hopital's rule,
Uh-huh.
it says, thus the responsive system at resonance, and at resonance means when it's at 1, right?
When omega over omega n is equal to 1. So anytime you have resonance,
We use equation
and you
3.15.
use that equation,
Okay,
okay?
that
You
helps
don't
me.
need to go back and
And
reproduce the
redo all
situation.
of
So you, when, okay, so when,
So we want to use
if you go to 1, use equation
3.115.
If omega is different than omega n, okay, then you use equation 3.9,
Yeah, and if it's the same,
and when it's equal to 1, then you use the equation
3.15.
3.15.
Okay,
You can you use 3.15 for all three conditions?
No.
Why?
Because,
Because 3.15 is just a version of 3.9, which is your x of h plus your
well,
xh plus xt.
not quite.
Or
3.1,
omega
3.9,
over omega n is 1.
3.9 is the general equation, right? It's
Yeah.
applicable to everything, technically, right? But
But if
when we figured out that omega is equal to omega n, we figured out that we are getting something that we are dividing by 0. So we're taking a different look at it. So the 3.15 is essentially a kind of a special case of that 3.9 equation. Okay? So meaning that you cannot use 3.15 if you have omega that is different than omega n.
So if it's less than one or greater than one, you still use 3.9.
Yeah, you could
Yeah,
use
okay.
3.9, yeah.
Sorry, so can we do one that's not three?
Which is one example that we can.
Yeah,
feel
I
like-
just wanna see an example, and
When it's
I know
not-
why I got hung up,
When it's
Okay.
not.
because I couldn't figure it out, but I just wanna see one that would be
Yeah, it's easy,
representative
yeah.
to the test that we could work through.
Okay.
So maybe
Yeah, that's,
A.
that is not a problem, but are you good with the 3-4 now? Or you?
I'll
you're
go
not?
back.
Now that we got that one, yeah.
Now that you
Now
have
we've
the
got cheat-
equation.
Now we
Yeah,
got
I'll
the
go
cheat
back
equation.
and try it again.
Okay. Okay. That is, let's see, if there is one in the book that mentions that. Chapter 3, right?
Yeah.
3 and 2.
Let's see. In fact,
One example from 3 and one from 2.
Anything that'll help us study for the test.
Yeah, that's all, I just want,
We want PTQs, possible test questions.
Or
Well,
like just.
like what you did in fluids and thermal and all the other classes. No, where you gave us like, hey, questions similar to this, and then I can, what I always did to study for your test was I'd look at the question you said, and then I would do the 3 above it and the 3 below it, just to get
so I'm
practice.
not supposed to choose, okay.
Yeah, no, I'm just saying,
No.
Don't make it harder.
I'm just saying something that I can do on my own where I can go into the book and just crunch through until I get it.
Several different examples
But
similar
in
to
the
it.
vibration book, it's not like that.
Yeah,
Vibrations all over the place.
Yeah.
Let's see if there is one.
Vibrate
I
full
feel
of-
like it really is.
So, let's see, chapter 3. Let's see if there is one, as you said, that has, I hate this book.
Welcome to our world.
Thank you.
I'm trying to find
There's
something.
nothing else out
Try
there?
hating it and not being good at math.
Well, maybe we can modify this, how about that?
Yeah, we modify.
We could
it.
do part,
Modify
you could do
Let's
part
go
A
ahead,
from
let's
it.
create
You
one,
could do
you
A.
know?
You can do part A from 3.4,
Yeah.
But it's still,
it's still equal to
it's
1.
still
Just change
equal
the-
1.
change the
Omega is
value.
equal to omega n, so we need to change the
Yeah.
value.
3.5.
So,
change
so
the
let's
value.
let's do this one as 30.
Okay, let's do it.
Okay, now that one we can use equation 3.9.
Too bad.
All right, so there you go.
So it's
So then the XH is.
So what is the equation, 3.9?
x of t is equal to x naught minus f naught divided by k minus
Yes.
mass times, that one, yeah.
That's this one.
So now
Yeah.
I plug it in.
Now we gotta plug it in.
So you've got the whole thing.
So,
So x naught here is 0,
Mhm.
You're literally plugging it
so
in.
we just plug it in, right?
Yeah.
That gives us the amplitude.
So, well, x0 you know,
It's 0,
0, 0.
f0 you know,
Mhm.
yeah.
k you know, m you know, omega you know. Now it's 30, it's not 20,
Okay, yeah.
right? Cosine omega, cosine 20t. Plus, this one is no. This one is no. There's nothing to be done, essentially. You're just plugging in the values, the
Right.
numerical values.
so once you find x,
And then you just get an x, so what the heck, let's just do it, with these initial conditions. So what is x? So this is x of, just to make sure here that I get the.
X is 0 was 0 and x dot was 10, or I don't know what the second one was.
Yeah, I thought it was 10.
No, this is x of t, by the way, not to be my mistake. This
So
is
you-
little x of t, you know,
Okay, yeah,
the
that's what I was,
solution.
yeah.
This is the
Otherwise-
solution. It's not the magnitude, it's the solution that contains both the homogeneous solution plus the particular solution. So you come in here, you go like x of t equals, what's x0 here?
0.
0 minus, what's
400.
f naught? That's 400.
Closer. Oh, yeah.
K is
4,000.
4,000 minus m is 10. Omega squared is 900, right? 30 squared is
Yep.
900.
Yep.
times cosine of 20t.
Right.
We're solving for t.
You're not solving for
We're
anything.
not
This is,
solving for
this is the
anything.
equation of
We're just
motion.
It's just what
Yeah.
it is.
So that's
Yeah.
what total response means,
Plus,
find the
yeah, the
function.
total response. So
Oh.
x dot 0 is what? 10 divided by omega n, which is, did we say 20?
20.
Sine 20t, right? Plus f0 is 400, right? Divided by k, which is 4,000 minus
10 times 900.
10 times 900 times cosine
Of
30t.
Right.
And that's the.
You know, when you simplify this, you get a little number, you get another number, but what's the idea behind it? You got the actual response. That means now you take t, you plug in any time, let's say 3 seconds, you know exactly where this, oh, I deleted that mass, where that mass is going to be. And from this equation, you can also figure out what is its velocity at that instant and that acceleration. So really, I'm thinking now, why should I give problem like this?
No.
You can just plug in the numbers.
The velocity and the acceleration come from the, do you have to use the energy equation?
No.
No, you just
no,
take the
no,
derivative.
no, no, no,
Oh,
no.
yeah, no, that's right.
No,
that's
no,
right.
no. This is exactly. Once you have this, you just differentiate once to get the velocity. You differentiate one more time to get the acceleration.
Don't.
But that's such an
math.
easy thing to
Yes.
differentiate, right?
What's that?
And that's such an easy thing to differentiate, right?
Yeah, of course. You
Well,
know,
first you have to simplify it to get it.
yeah,
But for this question, the total response is just x of t, right?
exactly. Total response is x of t, exactly.
So that kind of a question though, you might say, what's the amplitude, what's the acceleration, what's the velocity?
Well,
Well,
in this case, you cannot have that. Why? You cannot say what is the amplitude.
Because you got two parts.
You get different parts. Each one, it's not just one harmonic.
Yeah.
So
It's like how many harmonics do we have? Three of them. So there is not a single. In fact, it's not a harmonic motion anymore.
So would we be asked to find, like, I'm just skimming the problems in like 3.7, something similar, but it says find the amplitude of the force motion at the end of 1/4 cycle, 2.5 cycles, 5 3/4 cycles.
Yeah.
Okay, which problem is that? 3.7?
Yeah, I don't know if it's something I'd be on test, but just
Hey.
trying to get everything out of it.
If it attracted your eye, maybe you should look at it.
Thanks a lot.
Well, it's not a test, you're welcome.
No. We're
Yeah.
just trying things, you know? So what is the,
Spring mass system consists of a
Well,
mass
I mean,
weighing
you can
100.
use this one, right?
100 newtons
It's
with a
like-
stiffness of 2,000. The mass is subjected to a harmonic force, 25 posts.
I mean,
On its
but,
resonance
so
by
like,
Omega
you
n
take
is
this
radical
equation
force now.
to find an amplitude of force motion at the end of a cycle. A certain period, a
So-
certain amount of cycles.
so you got a weight, a mass weighing 100 newtons, and a spring with a stiffness of 2,000,
Yeah.
and the mass is subjected to resonance, okay, by harmonic force.
So it's equal to
F
1
of
there.
t is equal to 25 cosine omega t, means omega n and omega are the same. Find the amplitude of the forced motion at the end of a quarter and at the end of 2.5 cycles and 5 3/4 cycles.
So if it's resonance, we have to use equation 3.15 there, right?
That's correct. 3.15 is probably going to be the solution, right? Because it says it's a spring mass system subjected to resonance, and here it says the steady state solution, right?
Where does it say
It
that?
doesn't say steady state, it says mass subjected to resonance by a harmonic force.
By harmonic force, yeah.
Oh,
Well, you know, the
that's
particular
steady state
solution
as
is really the
particular,
steady
yeah.
state solution.
So, but I'm looking at equation 3.15, whenever I find it.
3.15, we have what?
So when you plug that in, you can find an amplitude at a certain. If I'm going down a hole that we're not going, please just tell me. But
Well, it's a good question, cause it's.
It is a good question, because we could find out what x of t was, the particular solution,
Mm-hmm.
okay, using 3.15, but how would we find out about the amplitude at the end of a cycle period?
Yeah, what does that mean at the end of one cycle? Because now you got, remember,
What do you
sine
apply?
omega t,
Natural frequency.
right? That means
You're going up and down.
two
and so-
pi is really the one period, right? And then another period, another cycle, another cycle, right? So you need to figure out, for example, for one cycle, what is the value of omega t?
omega t.
Yeah. Because the equation looks like 25 cosine omega t, right? So what is the period of for one cycle? Let's say at t equal to 0, right? The cosine starts somewhere, right? And then to come back to the same point, the value of omega t has to equal to what? 2 pi, exactly. That's the period, that's the angle of the stuff. So one cycle, omega t is 2 pi, 2 pi, yeah?
2 pi
That
t.
means a quarter of a cycle is
A
2
quarter
pi divided by
by
4, which is pi over 2. So that's what you need to put in, just substitute omega
Oh,
t
so
by,
you
pi over 2.
simplify, you get that.
Yeah.
You plug in pi over 2, and
yeah,
that's your
and then depending on which
That's your
cycle you're
amplitude.
talking about.
at wherever.
Yeah.
Okay.
Okay,
Yeah, 3.7.
that was actually a good thinking point, okay.
So, let's see. One quick question here. Can I erase this guy?
Yeah. That would be so nice.
I don't know, this is a random one.
It's one that
What
we
is it?
might need.
It's probably a homework problem. Why am I doing it? You don't need freaking homework. Something different.
You're basically saying the homework problems are good possible test questions.
Yeah. Let's see. What do I have here? This is kind of on chapter 2, but you have a spring mass system. Okay? It has a natural frequency of 10 hertz. It says when K, the spring constant, is reduced by 800 newtons per meter, the frequency is altered by 45%.
Up or down, we don't know. That's good logic, that.
Question? Find M and K. I was tempted to put this in the exam, so let's see what the response is. Of course, it's not gonna be there anymore.
Thanks
Why?
a lot.
Why? You can still
Yeah,
put
you
it
can
in.
change the
There we
number.
go.
Well, the
Fine.
natural frequency, we still have to go 2 pi times,
20 pi regions per second.
So think about this, you're given a,
This is a book question?
it's a
Chapter
book
2.
question, I think.
Which one is it?
Which
I
one?
think it's about 2, 3 or something like that.
Okay.
Oh, from chapter 2?
Yeah. So you have a mass at the end of the spring, okay? You don't know what the mass is, what the spring stiffness is, right? But if you reduce the spring stiffness by 800, if you reduce it by that, it says the frequency is altered. What the heck does altered mean? Well, we know what alters mean, but
Changed,
changed?
but up or down.
Okay, what do you think?
Doesn't
Do you think
matter.
it's gonna go up or is it gonna go down?
Where you're making the spring softer.
Softer, so it's gonna take longer to cycle.
Okay, see,
When it's
he
reduced.
threw in like this just to make you think. It's like, oh my God, 45% is gonna go up or is it gonna go down? You see, remember omega is equal to square root of K over M. So when K is lower, omega will be lower. So technically, you know, as you read the problem, you go like, I know it's gonna be reduced because the stiffness is reduced, right? So, anyone wants to take a little stab at this?
K is reduced by 800, so it's K minus 800, right? Minus 800 divided by the
You want
same
someone to go up there?
Yeah.
mass.
That'd be nice.
I can try.
Okay.
That's just got
Point 4.45 times
So we can start off with
W omega equal to
times 2 pi to get
25.
you know, I'm just gonna do 60 feet. And that's per second. And then we know that. Oh wait, is that the?
Yeah.
Yeah, W. But then we know it's K over N. So that's 62.83.
times 0.45, right?
No,
No.
It's altered by 45.
yeah, but we're not doing that yet.
Okay,
Yeah.
okay.
We're saying originally.
Yeah, find the
Yeah, and well,
Not necessarily divided.
well, we
but
could,
get rid
oh,
of it.
we could do,
Square both sides.
In order to get K minus by 800, you-
62.83. And we're trying to find M.
Mhm.
Well, you need to find M and K.
Yeah, but, okay, so
that's-
M,
That's
uh,
62.83.
K divided by 62.83. So then we
Square.
could just do, oh, yeah, you're right, that's squared. Thank you. That's about a second somehow. So then if we plug it back in here, we have, so we're trying to find our altered frequency, which would be square root of K minus 800 Newton meter divided by K times 62.83. Some, not simplified, something like that.
What if you put two equations and
Well, I don't know what I was doing. This is our new frequency, right?
Yeah.
Our new.
so 0.45
Oh.
K or 0.45
So the new frequency
omega
is
n.
reduced by 45%, so we kinda know that.
0.4
5
times
omega n.
62.83
Times the
times 62.
on this side?
Yes.
Yep,
Yeah.
yeah, you're right.
Times
Okay.
62.
62.83.
62.83 squared or?
No.
No.
No, oh yeah, yeah.
Flip that.
So now you just have two equations, two.
You have one equation and one unknown.
One unknown.
Yeah.
So then you just solve it. Maybe.
Close enough.
Someone might be able to explain it better.
Just solve
Words
it.
are hard for me.
Okay, so, you know, it's pretty close to what it's supposed to be, but I don't agree with one thing.
What don't you agree with?
It says the frequency is altered by 45%.
Oh, could we do?
Oh,
is
so
it-
one-
It's a,
1.45.
yeah.
So how much would it be, how much would it end with?
55?
With
Exactly, 55%, right?
Ah,
It does
So
not
this is-
say
One
that it's gonna
minus.
be 45% of the original. It was
Yes.
altered by,
Yeah, I would get that wrong.
I would get that wrong, I would
We
guess
all
that.
screwed that.
So this, you
Ah.
can put it back on the desk and we might.
So
Do you
one-
have the,
100
so,
minus
yeah, can you
45.
just work the number just to see if it's,
yeah.
so how do you work the number?
Does it say
Because
if it
that's
was
part,
reduced
part
or
of the thing
increased
where
from the
people have
45%?
problems.
Yes,
That's why I'm just like, there you go.
Yeah, you know, that's not the end, that's not the end, that's formulating the problem, it's solving it.
Okay.
When you have something equals to the square root of something, what's the first thing you should be doing?
Square both sides.
Square.
Both
Yeah,
sides.
yeah,
Yeah.
yeah, okay, wait. Square.
This is basically just, it's a math problem using vibrations
At this point,
formulas.
Yes.
we
Which
can-
is,
Yeah, oh yeah.
which is kind of frustrating. 'cause
Why would it be frustrating? It's,
I don't
it's-
know.
We're
it's-
engineers.
Engineers.
Because if you don't go through these,
Shut
you
your
are
mouth.
pretty darn limited as to how much stuff you're gonna be doing, you know?
So how do you know if the frequency is increased or decreased?
We said it was proportional, right? Omega is
Okay,
proportional to
that's
K.
a good question. So if you reduce the stiffness of a spring in a vibration, right? You're using a softer spring. What happens to the,
You said that?
I didn't say that, I'm just
okay.
asking.
No, okay, go ahead.
It slows down.
It slows down, right? When you put in a stiffer spring, it goes faster, right? So since here we are reducing the
Oh.
stiffness,
Okay, yeah.
so it goes without saying
Yeah,
that we're
yeah,
gonna be
I
out.
didn't finish reading, okay.
Yeah.
Well, I think what Doc was saying that was easier for me anyway, is to look at the equation where you say omega n equals root
Mhm.
that, so you know it's proportional.
Yeah.
So when K goes down, omega n goes up.
Yeah, I
K goes
didn't
up.
read the reduced by, I just saw altered.
I don't think I'm doing this right.
So,
No,
Yeah,
I'm
don't
not.
you have to flip the 3947 up on top?
Yeah, it would
Put that
be-
here,
Yeah.
and then that would cancel the K out,
Or you-
right?
You cannot cancel because of minus on the top, so. Like,
You're gonna have to do the math.
Oh, I have a calculator.
All right, so, take this over, here's 1194.5 times 3947.6089 over K. So you're gonna have to multiply that for me. Equals K minus 7. So you're gonna have a quadratic.
Wait, so
equation.
you're timesing it by that
I
one?
brought this over to this side, right?
I don't think I agree.
No.
I don't agree,
No,
you don't do
no.
it twice, you just take out the, you
No,
only
you
did it
see,
once.
you should, you see, I think you're reversing the stuff.
The K should be on top.
If you take this, you're saying the K should be over, even though it's.
Yeah, it should
taken on
be
the
K
other side.
over this, isn't it?
Yes. You're
Even though
taking-
it's, even though it's divided over here?
See here?
Oh, yeah, 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 yeah.
Oh, yeah, you're right,
That's what I
you're
was
right.
doing
So you're
wrong.
multiplying both sides
You're
by
right,
it.
you're right, you're right.
Math.
There we go. Think we're gonna get a quadratic there. 3, 9, you have to divide that.
Why do you have,
You don't need the extra one there on the other side, that extra,
yeah, you have
You have
1,194.
This
Yeah.
times this.
no,
Yeah,
you
but
wrote
look,
it over
it's
there,
on your other side too.
you can't do it twice.
What are you talking about? No, this is Clancy's equation,
Oh,
alright, and
Oh.
I just copied it over so I wouldn't lose it. I
Oh,
can erase it.
okay,
How's that?
and then you could take out the bottom.
Equals
yeah,
that.
take off the bottom.
Take out the denominator there, okay?
119.
Now you add 800,
But-
First we do this.
Yeah.
Yeah,
okay.
You gotta
That
multiply
one
that
there.
first.
Okay, so K over what?
1194.15 divided by,
Yeah,
This one divided by that.
39476.
What?
What is that?
1194.15 divided by 3947.6089.
.302.
0.302
0.302-ish. Okay.
equals K minus 800. So So we say K times 1 minus 0.302 equals 800. So K equals
Oh.
800 over 1 minus 0.302. Boom.
Oh, and we're right back to 1,146.13.
1146.
Yeah.
That's about right.
Point what?
13.
Good. See, it's a little,
It's tricky because A, you have to recognize that it's 1 minus 45.
That was the trick there.
yeah, it says it's altered, you know, when I looked at that, I said, yeah, it's good.
Kind of
Why-
ambiguous.
Could
You
you
know,
explain what they
ambiguous.
did up there, please? So
All
we
right.
know that's what's not.
Yeah, maybe you go through it.
Yeah.
You should go up there.
Yeah, show us your Yeah, right, I don't even know.
Well, my steps, if I were to do it, this is
Yeah.
what I would do, you know? It says the spring mass system
2.3.
has a natural frequency of 10 hertz, meaning that obviously omega n equals 2 pi f, right? Which is exactly what we have
So I
there,
started out.
which is 20 pi, okay? Then I go, okay, I don't know what m is, I don't know what k is, right? But I do know that this 20 pi is equal to square root of k over m. Okay? So it's one equation, in my thinking, it's one equation, one unknown, cannot do much with that, right? So I'm just gonna write it as 400 times pi squared is equal to, I don't like to have square root in my thing, right? Is equal to just k over n. Okay, my first equation, right? And I know that I need to find another equation to solve for the system, right? My second equation is coming from what we were told. It says that if you reduce this by 800, that means I'm going to have k minus 800 divided by m is equal to how much? 0.55 times this 20 pi.
Squared.
No.
It's not
No,
squared,
no,
no,
it's
it's
not
not
squared.
squared.
Not yet.
Now I'm
Okay.
gonna go
Oh,
back
okay.
and square
Square
this,
both
right?
sides.
So 0.55 squared times 400, I don't have a calculator, that's why I'm doing it this way, times pi squared, now square both sides, equals to k minus 800 divided by m. So this is my second equation. Okay? So how am I gonna solve this? I don't need to do any of this stuff. I just divide this by that. If I divide this, let's say I divide this one by this one, what do I get?
No,
No.
that's,
Oh, well.
you get point.
You get-
0 just 0.55 squared
5 squared.
is equal to this divided by that. That means k minus 800 over m divided by k over m or multiplied by
I'm over
Okay.
K.
by m over k. See, the m cancels out, right? Now I get pretty much the same equation as you guys have. What's 0.55 squared?
0.3025.
0.3025. And I multiply here by k is equal to k minus
Yeah.
800. So I will have then k, you know, I bring the 800 to the other side, it becomes plus 800, right? And then factor out the k, 1 minus 0.3025. And this is, it's probably the same thing you
Yeah,
have,
same thing.
Pretty close.
1,146.95.
which
So
is,
this-
which is the same thing. And from here, k will be 800 divided by that. So, it's, the solution is fine. Is it kind of clear? It's
Yeah.
two unknowns that are in the problem. We need to have two equations. the first equation comes from the natural frequency of the system as is. And the second equation is the natural frequency that was changed based on reducing the K value.
And that's it. That's all in on exam.
That's
2 questions.
two questions like
That's
this.
2 of the 4 questions.
Oh, no.
So there's 4 questions on the exam?
Well,
We
we'll
haven't
see. I
voted
have
yet.
to work on
Wait,
it
wait,
based on
but-
what I'm seeing
Just
here.
stop
you know?
asking.
We could do a take home.
Yeah.
Yeah,
They know.
Then you could make.
Maybe for the final.
Yeah.
Wait,
Yeah,
you already
thank
said
you.
for the final.
No, at least you go
Maybe
like.
for the final.
We need that.
Don't piss him off.
No, he's pretty calm.
It's a very nice shirt you have on, sir.
So, let's see. Quick question again here. That's a nice one. Can I erase this?
Yeah. We can work on the test together and get one score.
Open neighbor.
Open neighbor.
We probably still get a seat again.
Yeah.
We fight.
So,
You're an idiot.
so you got a spring mass again. Where K is, M is 10 kilograms, and this is 5,000 newtons per meter. What is the question? It is subjected to harmonic force. So subjected to harmonic force of amplitude 250 newtons, 250 newtons, and a frequency of omega. It says, if the maximum amplitude, if the maximum amplitude of the mass is observed to be 100 millimeters, comma, what is omega? Find value of the exciting frequency.
What number is this?
What number is this? 39.
3-9. First of all, should we write the equation of motion, or the equation of the system?
Isn't this one where we plug in the value for X and then we just,
Yeah.
Yeah.
So it's not necessary to do equation of motion that we're just wasting
Time?
time.
Okay.
Because really, what is given to you here? The maximum amplitude,
Oh, so that's
okay?
what is that?
So the maximum amplitude, which is that capital,
X
Big X.
Yeah.
the
Big
little
X
X, that big X,
Big X is a maximum?
yeah.
So,
amplitude.
Yeah.
X is
I
equal
guess
to
there's no
250.
T in there, so
Yeah.
it's just the max.
Exactly, that's the maximum amplitude. So we know what the equation for that amplitude is, right?
That's that F naught thing.
That's
It's
the
3.28.
cap X, right?
Yeah, is equal to
3.28.
Equation 3.28.
F naught divided by,
It has 3 different forms, but I think one of
Oh,
them is
yeah.
F naught over K minus M omega squared, something like
Well,
that.
then delta static over 1 minus.
Or F or delta static over
The-
1 minus
then we'll.
omega squared over omega n squared.
See, right, fine, it's no-
Either way, you know.
F over,
Yeah, X, F naught over K minus M, that boom. That's
yeah,
the one.
that one looks good. But do we know F?
Yes,
Yes.
250.
Okay, so,
250 newtons.
so,
Yeah.
So 100, 250. Boom.
Oh, wait.
we have to,
The maximum amplitude.
I don't think that's gonna, we don't have enough
You
information.
never heard that? What's wrong?
So you said that to 10,
100
yeah, 100,
equals-
well, no, that's millimeters. So
Oh,
you just,
point one.
point one, yeah. So you're solving for that, yeah.
Well, I guess there's nothing wrong with that. I was just looking at it the wrong way.
Oh. Oh, I see, okay.
Divided by minus 10. Square root of is equal to, is that
So
the
what's
right?
omega?
Is that the right
15.81?
omega?
14.81.
And that
We
is
get 200.
radians per second.
I would just multiply
It's
this out.
in
No.
radians per
So
second,
That's
yes.
okay.
700 times.
If you have, if you've gotten
5,000.
1581,
So we'll say
You're
5,000,
good.
so
Where did you say?
15.81.
15.81, I'm sorry.
Yeah.
I just multiplied this out.
That's what.
Brought this over this side.
Oh, what is,
Yeah.
I
what
went
do
times
you use for
5,000,
F?
so you get
So F
500
naught is your 250.
one.
That
Omega squared, 250.
remember, see, that's, I'm glad you asked that question, you know?
Yeah.
Because F naught's the forcing
Exactly.
force.
It's the forcing force. What does it say here? It says here it is, I'm pushing on this mass with an amplitude of,
Oh, I didn't give that.
you see, nobody's gonna
Wait,
always,
what?
Amplitude,
Yeah.
I
Now,
think
why do they
amplitude, I
say
think meters, I'm
amplitude?
looking at meters, and it
Right.
says newtons.
Wait.
yeah. Amplitude of, yes, it, sorry.
When did it say we're
No, no,
pushing on it?
the force, yeah.
That's force,
The
yeah, I
force
don't
is,
think of amplitude as
Newton.
force, I think
Yeah.
of force is force.
Yeah.
okay.
There's harmonic
Amplitude,
force and
amplitude
amplitude.
is not distance. Let's agree on something
In a
here.
forcing function, right? It's
Amplitude is only distance when you're talking about x of t, right?
Yeah.
If I talk about here x of t, is, you see, it all creates new discussions, which is nice. You know, x of t is equal to a cosine omega t, let's say.
Yep.
Okay? What does a represent? The amplitude of the displacement.
Yeah.
If I take x dot of t, that should be equal to negative omega a
Sine.
sine omega t, okay? What does omega a represent?
velocity.
But what?
Oh, the amplitude of the maximum
It's still
velocity.
the amplitude of the velocity,
Yeah.
right? And then x prime prime is minus omega squared a cosine omega t. So this is the amplitude of the acceleration. So the word amplitude does not necessarily mean distance. It just means whatever multiplies that cosine or sine function. Why? Because when you have x of t, or I don't care what the heck this is like f of t, right? Function is equal to f0 cosine omega t, right? This is the forcing function. And it tells you, so what is this one?
250.
It's the amplitude of the forcing function,
Where did this
okay?
question
That's why
say
it's in newtons, okay?
forcing function though?
So this word amplitude does not necessarily mean
Subjective
distance.
amount.
It's whatever multiplies this, because by looking at this, we know that the maximum value of the force is going to be what? It's whatever F0 is, because cosine is always between -1 and 1, okay? So don't let that unit here throw you off, right? In fact, if I were to write an equation for this, what would it be? Well, f of t is equal to 250 times,
Cosine omega t or something.
okay? This and these two statements are equivalent. Right? So, what is the equation of motion of this system now? Of course, it's not there. The equation of motion would be,
mx double dot plus,
so 10
oh, sorry, 10x double dot.
X double dot
Plus 5,000.
plus 5,000
x equals
x
250 cosine.
equals 250 cosine
15
omega
point.
t,
Oh, okay,
right?
15.81. Whatever, I would just put something in omega.
No, but this omega is, well, once you find the
We
solution,
solved
yes,
omega,
yeah,
right?
after you solve
Yeah.
for it, yes, yes. It's 15.81, thank you.
We don't need that to solve the problem, right?
We don't need what? The,
This, in x dot.
this one? No, you don't,
Yeah.
no. No, I'm just trying to kind of,
Connect everything to us.
try to kind of train you to, when you look at a differential equation, don't just look at it as an abstract thing. Sometimes when you look at it as it's like a mass attached at the end of the spring and the other one is damper, right? It kind of makes sense when you look at the solution. That's all. I'm trying to connect the dots, that's all. But you don't need this to find the solution, right? What else? So that's that. Let's do something else. Let me erase this guy. So again, spring mass. Where the mass is 50 kilograms and the spring is 5,000 newtons per meter. It says find the following. Find A. CC, I guess the critical damping. B is damped natural frequency.
You gotta show a damper in there, right? In your
Damped
drawing.
natural, let's see here. Frequency, of course, yeah, there's gonna be a damper if there is a damping. When C is equal to CC over 2. And the third one is what is the logarithmic
Oh boy. This is chapter 2.
decrement. Anyone remembers what the logarithmic decrement is? Teacher?
Huh?
The logarithmic decrement.
Isn't that's the attenuation.
At the attenuation, so when you look at the logarithm of the first amplitude to the one just next,
Okay.
and it should be decreasing. So
Right.
it tells you, and it's usually, and that is a function of the damping. You know? And people, I think when we took that lecture at that point, we said that's usually used to figure out how much damping you have in the system. Okay, so it's important to be familiar with that equation. The equation for the damping, I think, is two.
Or this problem.
Oh, this problem, what the heck this problem is, it's 1003.
2.103?
Yeah.
Is it 2?
0 point,
2.10.
2.10.
Oh.
2.100.
103
Yeah,
in chapter 2.
chapter 2,
Yep.
yes.
Okay.
Okay.
all right.
If you guys wanna take a little break, you can, you know, maybe rejuvenate a little bit.
What? Oh, 2 times, yeah. Meters times newtons, or times kilograms.
Glass of water.
Meters times kilograms.
The zeta was CC over C, right?
What's that?
The zeta, is it CC over C?
Zeta? It's the
C over
opposite.
CC. C over CC.
CC.
Okay.
I don't know if my book with me, which is a problem, but. ICC, okay.
Let me see.
C over CC.
Yeah, we can.
No, C equals CC over 2. We find CC and
Here.
Square
you guys get to the decrement, let me know what value you want.
Yeah. Do you know what equation number that is?
2.85.
2.85, thank you.
Delta equals one over x2.
Oh, wow. How do you know if it's logging?
I guess it means that when it's going, you've got one amplitude and it's damped, it's gonna be a lower one, the ratio of the two.
Yeah, how do you
Is that-
find?
I'm wondering that myself, I'm waiting.
Oh.
Next one's gonna be 2 pi 2.5.
So that's the ratio. What is this? Oh my gosh. I feel like
There we go, zeta, omega, and tau d. Tau d. Period. Advanced period. I'm guessing.
Working on it.
We're ready, Doc.
What's the number?
For which?
A is a thousand.
How about delta?
Delta, delta, delta.
I mean the decrement.
I don't know that one.
Oh, we're waiting for that, we're waiting for you to go through that one.
3.6. Pretty close. Yeah.
2 squared.
And what did you get for,
You got 3.27,
3
or
point?
3.6,
326.
3.27.
For the.
3.63, if you got 3.627 or 3.63, you're in the right.
I don't even know how to do part C.
You have the equation.
Yeah, but it doesn't mean much to me right now.
What do you mean? Look at the equation, what does it
So
say?
can I
Delta
use,
equals?
can I use
Break
2
time?
pi times, 2 pi over W?
That's what you're supposed to use.
Oh, well,
Because,
okay.
you see, that equation always starts with, it's the log of, I think, x1 over x2, but that's your, it's telling you what it's coming from. But they have worked out already that ratio.
So that WD, that's, is it still,
What's omega D?
It,
Then
is it still 2
1 minus
square root of?
zeta squared.
It's the damped frequency. Yeah.
The closer it gets to 2,000.
It's omega n
Is it
times
8.66 or something?
That's what it said.
8.66, yes.
Wait,
I did my math right.
It's omega n
times 1
Yeah.
minus zeta
times
squared. Square root of 1 minus zeta squared.
the square root of 1 minus zeta squared.
okay.
The definition of
Zeta
omega
is
d,
0 to 60.
the damped frequency.
And then to get to the logarithmic decrement, we know that delta static equals ln
It's one of those.
x1 over x2, which equals whatever that hell that was.
Zeta squared,
Zeta is just C over CC.
Zeta omega n tau d. What's tau d?
It's what you just said, the square root of 1 minus.
That's omega d. That's not tau d.
Oh,
it's negative.
don't use that, just use this.
Oh. 2 pi over omega d times zeta squared. So,
And what is this Zeta? It's just C over
That's
CC.
C over c.
Okay.
So he gave us the c over c wherever it was.
Well,
No,
what
it's-
Are you gonna
is-
use an equation 2.84?
Yeah, 2.85.
No, yeah, 2.85 is
And
easier
it's
to.
that last part.
2.85, right to the end of
Yeah.
2.85.
Yeah.
So,
Easy as possible.
so just so I'm getting my head straight, C equals CC dot, we figured out CC was 1,000, so divided by 2 is 500. So it's 500 over, zeta is 500 over 1,000, or 1/2,
Sure. Yeah.
okay? Okay, so this
Squared.
WD here is, it's not W, it's omega, but anyway, 1 minus 1/2 squared, right?
Yeah.
Square root of that. I find that out, I put that over here.
What do you got written down here?
This is,
That's
Omega D.
omega n times that. So don't forget to multiply the square root of k over.
oh, omega n, yeah. root of K over M, oh boy.
This is 2 pi over omega d.
0.458-ish, maybe?
You slow down.
You need to write neatly.
I would say where, I would say whatever you're good for.
So what is the solution to this little guy?
Is it 68.59?
3.6,
Which little guy?
this little guy back here, this problem. So what is CC equal to?
1,000.
2 square root of Km, right?
Yeah,
2 square root of 5,000
that's 50.
times 50. And that should give you 1,000. Okay, and what is the unit of CC?
Newton
Kilogram per meter.
Newton,
Newton second per meter.
Newton second per meter. Yeah. Because, why is it? Because remember, F is equal to C times V, right? So this is Newton, this is question mark, and this is meters per second, right? That means that the question mark is Newton, I multiply on both sides by S over M, and therefore you get an S over M. That's dimensional analysis. Okay, so Newton second, so that's first question. Number 2, what is the, what was the second one?
Damped
What is the
net.
damped natural frequency when C is equal to CC over 2? That means that C is equal to,
500.
C is equal to CC over 2, that means that C is equal to 500. Okay?
Yeah.
And that means that zeta is equal to
1/2.
1/2, 0.5.
0.5.
That means that omega d equals what? Omega n
Times the square root of 1.
square root of 1 minus
1.5 squared.
1.5 square root. But what is omega n?
Square root of k over m.
Okay, square root of k over m, which is 5,000
10
over 50, that's 10,
Yeah.
right? Square root of 1 minus 0.5 squared, this should give you hopefully
8.66.
8.66
Yeah.
radians per second. And C, the logarithmic decrement, I think the symbol that we use for that is delta. And the equation is 2 pi divided by omega d times C over 2m. Now we have all the quantities, right? C we know, omega d we know. So when you plug all those values, you find something like 3.627, roughly.
Not bad.
Is that unitless?
Is that unitless?
Should be
It's
meter.
the
Red.
log of
Yeah.
this displacement over the displacement. So
Yeah.
it is unitless.
Dimensions.
Yeah. All right, one more one. That has,
Can we,
can we,
this is bugging me, why am I getting why am I off by a decimal place? I'm getting 36 point something.
36 points?
C over 2m is 500 over 100, right?
So, C,
C over
okay,
2m is 5.
2 pi over omega d, which is 8.66. C is 500
Over 100.
divided by
5.
2m, which is 100.
Yeah.
So this is 5.
Oh, it's because I divided by 0.866. Never mind,
I-
don't mind me.
Yeah, that's the decimal point off.
Can't take you anywhere.
We still have to do a lab. Eek.
Yeah, the lab is not very.
Yeah.
Yeah.
I don't need it. Cause I can't pick it up either.
Air duct.
Midnight.
This one right here.
Which one?
This one.
Plus I'm like, can't send it.
So you say.
I know,
There's some fine print for you.
Going past the drop.
He said he didn't know there was gonna be
You
massive.
should be able to see what
class.
your first test is graded before you, so you can draw.
I haven't started chapter 3.
Let's see, what do I have?
Yes. What part of that, right? Yes, I mean,
Why? Because of law.
So they want it in the front.
1/6.
They want it up, so be
not
there.
when June comes.
Sick of heart. But
Yeah,
basically,
yeah,
it's
yeah.
hard to
Because-
do those because-
I know when I'm excited.
I'll be down with it. So what's gonna keep it from flying out when they try to lift it out? It's like, super cheese.
So when
Oh,
do
yeah,
we
you
start?
guys are gonna wanna go in and set that up.
We're gonna die.
I'm thinking now it's not gonna be a simple slip out, you know, like, something bad is gonna end up on. And you guys gonna go flying all over that.
So no dinner tomorrow, why do you need?
I mean, we'll do it, but I have to figure out.
Just go there, oh, I gotcha.
Oh, God.
Really,
Which
so
one?
to not,
The wind.
You think it's happening?
no, only husband
What?
and the kid,
I
not me.
mean,
Huh?
But tomorrow we stay
They
home.
leave tomorrow?
No, they leave on Saturday morning. And,
Oh.
so we're gonna have hot. We decided to have something at home because Friday night it's kind of busy and, you know, with kids and stuff, it's hard to travel. So we decided Huh?
Yeah.
Yeah, right, and that's why it's not working.
Forget about Valentine's.
Take care. Yeah, I don't care.
Chris, you feel better? What, next week?
No, are you feeling like
Oh.
physically, are you?
I don't know.
What the hours ago?
Stopped puking last, yesterday at 2 AM.
I think it was a good.
Good review.
No, I don't know.
Change
We're 2 days in a row.
Change the numbers, huh?
Whatever we review and you just change the number.
Can this, what we did today, be the test?
Really?
Yes.
I don't know
You
how.
didn't eat that.
He's gonna
We
keep
can keep
making
a
it
secret.
worse and
His
worse.
test, how about
Pushing
that?
the envelope here.
Take home.
He's gonna make it worse.
Let's start reviewing,
Yes.
if he's reviewing more,
So
than
antagonizing.
whatever he review, it's not on the test.
Trying to stay away from the complicated problems. That's all.
Thank you.
As
let's
long as
do-
they're not on the exam.
Let's do one more.
Just, it's not any
You're one to talk.
So you have, it says the forced response. So forced response of a 1 degree of freedom system is going to be given by this equation, 3x dot dot plus 12x equals 3 cosine omega t. Okay. It says, question here, it says compute the magnitude forced response. For the two cases which are, which have omega equals 2.1 radians per second, and the other one, omega equals 2.5 radians per second. Okay? And that's the first question. And then the second question, comment on why one value is larger than the other.
Is this in the book?
That's not from the book.
We have to do both the homogeneous and the, particular piece, right?
The forced response is gonna be the X of T equation.
Yeah, the XP of, yeah, XP of T. The particular solution is really the key solution to those types of things. So we know, been getting back and forth on these types of problems because X value should be known, even for, I mean, for the end-damped one should be like that. Or you should be able to know where to find it.
We're getting kinda lost in the wording of these things.
Okay.
I mean, when we go through the book, we're talking about the particular solution,
Yes.
but then like forced response, like, what does that mean? I don't know.
Forced response is the general response, you know, compute the magnitude of the forced response of the two cases. That's the forced one is really the particular one, because that's when you have a damped or undamped system that you start vibrating. The forced one, you know, the forced one is the steady state one, if you will. Remember, the other part always kind of dies out, you know, the one that is in between.
So it's the steady state?
Yeah, the steady state is the forced. The books call them all different things. The homogeneous one is the book calls it the transient one, right? The one that dies out. And then what remains is really what you are pushing on the thing. In other words, the mass is eventually going to vibrate at exactly that same frequency.
So you just look at this and say, okay, this is undamped forced vibration, and go and look in that section in the book to find out.
Yeah, I mean, it's, you probably notice from there that it is undamped, so the problem does not need to tell you that it is undamped because you don't have an X dot. There is no C, okay? So those are the subtleties of these types of problems, you know? Somebody gives you that, you should determine from looking at that there is no damping.
It's section 3.3.
It is section 3.3, but I'm trying to figure out what formula to use.
One for X.
Remember that X is equal to F0. First of all, what is F0 here? Equal to
3.
Yeah, there you go. What is M?
Three.
What is K.
12.
Yeah, that's how those are your connections. And using that type of information, one of the things that you always need to do is try to figure out what the heck is omega n, right? What is, you know, you probably don't even need that in this particular problem. If you use that form of x equals f naught over k minus m omega squared, that's one of the forms.
Mm-hmm.
You know, if you can keep it that simple, you can figure out what the, what x is going to be.
3 times 2.1. I need to bring my calculator and I didn't bring it.
I think this is gonna be our last topic, because we still need to do a lab, as you guys said. So has anyone computed the x's? At least for the first one, what was it?
Minus 2.43.
2.43 is a good number, yeah.
Second one is 0.44.
0.44, that's a good one, yeah. So the first one is about 2.44, 2.43, somewhere about 2.44. And the second one is 0.44. That means if you are exciting your system with the lower frequency, you are getting
Bigger amplitude.
bigger amplitude. When you go to higher, you're getting lower. Why is that?
It's proportion to the inverse square of the frequency. Omega.
What was the first number? Because you're getting further away from the natural
2.4.
frequency.
What did you say?
You're getting further away from the natural frequency.
Exactly, that's the whole idea. And what is the natural frequency of the system?
The frequency square root of 12 over 3, so
Which
square root
is
of 4 is 2.
Which is 2. So the natural frequency is at 2. The first frequency that you calculated is omega equals 2.1. That's closer to the danger. That's why the amplitude was high, right? When we went to 2.5, we were a bit farther from 2, and therefore the amplitude went down. That's kind of the logic behind it. Any question as to how this is done? Well,
Just talking about some good point. The previous problem, they said find the amplitude of the force. Now they're saying find the magnitude of the force. It's just the wording is really like once someone explains the form, it's like, oh yeah, okay, those are the ones I'm supposed to use. But it's like,
Yeah,
why
the
can't they
wording
just
is
say
not good,
Yeah.
find X?
It's like-
I mean,
well, you know,
or you
I
at
was
least use the
not
same verbiage they
equating
use.
These
in
are-
I was equating the big X to amplitude, not the magnitude.
well,
And so now I'm seeing the word magnitude, I'm like, okay, where is that one?
the magnitude of the forced response,
Did not come easily.
it is, oh, you didn't make that connection?
No,
Yeah.
I had to ask Brian.
Consistent language would be nice. Yeah.
But this is, again, I don't know you have, there are different, unfortunately, references to the same thing sometimes.
And we could have said the amplitude of the particular
Like square it as
solution,
well.
and they'd be meaning, they'd
Oh,
be asking for the
no,
same
yeah,
thing. It's
they
like-
wouldn't.
It's like, well, what do you
Yeah.
want, like,
Yeah, they
because
wouldn't.
I'm used to learning, oh, that's a particular solution, that's the
where
amplitude
I
of a
was.
particular solution, it's like,
Yeah.
they keep changing
They,
the words
they,
on.
they like to keep it kind of vague like that sometimes. Maybe it is on purpose, I don't know, because you see them all over the place. And on the same book, you find it sometimes they call it magnitude of the response, which in the eyes of a lot of people, it's the response versus the magnitude of the response are two different things, right? When you talk about XP is equal to capital X cosine omega t, right? This is the response, okay? Now, when somebody says, okay, what's the frequency of this response? That's omega. What's the amplitude of this response? But sometimes the amplitude is also called the magnitude. You know, it's the length, it's how high it is, you know? Like in vectors, for example, what is the magnitude of the vector? Have you heard any other people say the length of a vector? Do they mean the same thing? It exactly means the same thing. So it is the language. We're not creating that language. It is what it is.
No, it's okay.
So in this particular problem, you have x equals, I think it's f0, right? Over k minus m
Omega squared.
omega squared. So that's what you are trying to figure out. And then for the first one, obviously f0 is equal to 3. So the first case, you're going to have 3, right? Over k, which is 12 minus m, which is 3, times omega squared, which is 2.1 squared. I have no idea what this value is.
Negative 2.4.
2.44, something like that. And number 2,
It's negative, right? So
well,
It's absolute value.
if it's negative, but if it's the magnitude, it should be the absolute value of that, but you know, not
You're not
that.
gonna dock point if it.
I don't dot points if you put negative or positive, you know, it's, but I think that's why you probably put in magnitude,
Gonna
because
hold
he
you to
knows
that.
that you're gonna have this or that, right?
What's up with your sign?
And then B,
Will be on mine.
B will be 3 over 12 minus 3 times 2.5 squared, and then this is 0.44. And then remember what the idea is that omega n is equal to square root k over m, which is equal to 2 radians per second, right? This solution of A is at 2.1. The solution at B is at 2.5, right? So this is closer to the resonance, right? That's why the magnitude here is high. Or that's why the amplitude is high, is higher than it is in here. Because remember, when you go like this is omega n, you know, come in like this. So that's,
Boom.
and
That's good review.
I don't suppose you could email us
Well-
with some other example problems.
No, I wish, I'd have to go search now for some problems.
So if we were studying for the test,
If we were studying.
well, when
If we
we
were,
study,
as if.
and we don't have time to do every single problem in the book,
You
How
should
would
not be
you-
doing all the problems in the
how
book.
would you like,
Read out.
how do we study for this test? How do we prepare?
How you study for
Chapter
that
2 and
test?
chapter 3.
Look at chapter 2, look at chapter 3. Don't try to,
That's that's over 150 pages.
Yes, I
Don't do all the
know.
problems,
All
look
the
at the
problems.
chapters that are 200 pages.
Chapter 2 talks about the three cases of the damping, over damping, under damping, and particularly damping. And for under damping, you need to know about, what is it called? The the frequency ratio, the zeta, how to calculate that. You need to know how to calculate the critical damping. You need to figure out if the system, how a system can be under-damped, critically damped, and over-damped. And if a solution, if an equation is given to that, you need to be able to apply the initial conditions to it and get the response. Okay? Now, that's for free vibration. That's pretty much it for chapter 2. You know, there isn't like 1,000 things that you need to look in chapter 2. You also need to look when it's damped. Problem that we just looked at, what is the logarithmic decrement? You need to be familiar with that, right? And what is the equation that is associated with that? And then in chapter 3, aside from all the issues of square root, omega n is equal to square root of k over m. Sometimes when you change k, when you change m, how does it affect the natural frequency, and be able to find some unknown stuff. Like earlier, we had an mk, and then we changed just the k, and then based on the change in natural frequency, you're asked to find what is the mass, or what is the k of the system. And the only equation that we used for that one is just the equation for natural frequency, that's all. And be able to manipulate that equation to find that. For the forced vibrations, you need to be familiar with the amplitude of vibration, right? And
Slash magnitude.
slash magnitude, whatever you want to call it. So amplitude or that, but that's really the response that, right? And then be able to use that equation, that we had, the 3.9, I believe, 3.13. In the event, the frequency is the same as the natural frequency, and navigate through those. So, there isn't much else I can say.
We wouldn't tell.
So today's lab, which I have already set up, by the way, before we go there, it's a lab that's in which we're going to be putting in a mass at the end of the spring, right? And then we're going to put in our sonar in here, right, to record the trace, right? And I figured out yesterday how to kind of put that in the center, so that when we get the position, instead of it starts at something that's other than 0, it's going to start actually at 0. So you're going to see the amplitude here, or the magnitude directly from here, right? From the trace. So what we will be doing is we're going to take this guy and then pull it from equilibrium, and then see how it vibrates. Okay? So because it is undamped, technically it is undamped, in the trace of that the Logger Pro is going to record, we're going to try to fit a curve through here. Logger Pro is going to do the whole thing for you, right? But what kind of function are you going to choose for this? It's either a sine function or a cosine function. So once you choose that, the Logger Pro is going to tell you exactly what that equation is going to be, okay? Which is nice, because that frequency that the Logger Pro is going to tell you would represent what kind of frequency you take in this case.
Come on,
It's the natural frequency of the system, right? And then the maximum amplitude here would be the magnitude of the maximum displacement. Then, because the title of this lab is damped vibration, we don't have anything fancy to do fired vibration. So what I did is I created, then we put in on the mass here, we put in kind of a paper plate underneath.
Air damping.
It's air damping, some air damping, right? So we'll put it there. Hopefully it does not affect too much the mass, because it's the thing. And then we're going to repeat that same. experiment. When we do the experiment, you're going to see a trace that's gonna look like this. It's not gonna be this big because it's air damping, it's not gonna be the big one, right? But what we're going to do is just fit a curve through this. If you want to fit a curve through that, what kind of curve do you think we're gonna be fitting? It's not a log. It's a decaying exponential times a cosine or a sine, because that's how the under-damped response is going to be. Once you do that, the program is going to tell you what this frequency is and the rest. And by the way, if he gives you that frequency, what would that frequency be?
Omega D?
It will be omega D, exactly. That's the damped frequency, which hopefully is going to be less than this frequency because there is some damping.
Otherwise we did something wrong.
And then from there, you know, when you get omega D and you know omega N, what can you find from this system? Remember what the relationship between these two are?
1 minus zeta squared.
Omega D equals omega N times square root of 1 minus zeta squared. Now, if you know this, you know that, then this equation will allow you to find
C over CC.
zeta, which is C over CC. Now, do we know what CC is? Because we know the M, we know CC is square root of, 2 square root Km. Now, we can figure out what the damping is.
Cool.
Are we
That's
gonna
it.
do the viscous part?
That's what it is. Yeah, we're gonna do first we're gonna do it without anything. Then we're gonna do it with a 6-inch or 8-inch, I forgot what the size of that plate is.
Yep,
And then we're gonna do it with a bigger plate,
with the cardboard.
with a cardboard. Okay.
We're not gonna do it with syrup though, right?
No, we're not gonna
Water?
do the syrup, you know.
So ignore part 3?
Well, the part 3 is just an observation. I think we're just
Okay.
gonna cup of something and then we'll just see how it dies down. But you don't do any calculation or anything like it, you know? Because air damping is,
Better
you know.
pancakes.
Okay, so